Hi and welcome to this video where we get to talk about naming alkynes. It's been an awesome series thus far where we've dealt with naming organic compounds. We've dealt with the alkane functional group, the alkene functional group. We saw loads of exercises and now we're on to the next one, which is naming alkynes. Without further ado, let's go into what we have for today's video and see if we can do justice to a thing or two. So the first thing we want to get out of the way is by knowing what an alkyne is. Okay, so what is an alkyne basically? An alkyne is an hydrocarbon, okay, that contains at least one carbon to carbon triple bond, one, two, three, between two carbon atoms. Now, alkynes have a general formula CnH2n minus 2. What this simply means is if I know the number of carbon atoms that are present in an alkyne compound, then I can determine what the molecular formula will be. So for example, let's say I have two carbon atoms present in an alkyne. It means CnH2n minus 2 becomes C2 because anywhere I say the number n, I replace it with the number 2. H2, now instead of n, I put a 2 as well, and then minus 2. All of this goes to become C2H4 minus 2. It finally becomes C2H2. That is how alkynes work. And you can see the structure denoted over here. Two carbon atoms and two hydrogen atoms. So that's how the formula comes into play. So they use the suffix, finally they use the suffix yne. It is pronounced as yne. Okay, so the triple bond controls the numbering priority over alkyl substituents. For one triple bond or for alkynes that contain one triple bond, the general formula is CnH2n minus 2. So now that we know what alkynes are, it's also important to know the step-by-step procedure for giving them their names. So the first thing to do when you want to assign a name to an alkyne compound is to choose the longest chain that contains the triple bond. So we have this structure denoted over here. The first thing to do would be to choose the longest possible chain that contains this triple bond, as you can see over here. So we could start by naming or by counting from here 1, 2, 3, or we could count from the right to the left 1, 2, 3. Now, counting from the left to the right gives this double bond to carbon number 2. Counting from the right to the left gives this triple bond, not a double bond, triple bond to carbon number 1. So our right counting procedure would be from the right to the left this time. Did you see how that was carried out? So step number 1 is to choose the longest chain that contains the triple bond. The parent chain must include the triple bond, even if another chain looks longer. Students must always check this carefully. So step number 2 would be to give the triple bond the lowest number possible. Now the triple bond always carries priority over alkyl substituents. We'll be looking at examples where there are substituents present in an alkyne compound. We'll be seeing how that can be named. So we have this example on the screen. You can see carbon number 1, carbon number 2, and carbon number 3. If we count from the right to the left, we have carbon number 1, 2, and 3. So we will count from the left to the right because this triple bond is given to carbon number 1. If we count from the right to the left, this triple bond would have belonged to carbon number 2. So we're counting from the left to the right. Now, counting from the left to the right, we have 1, 2, 3. 3 carbon atoms gives us the parent name prop. Now, the triple bond is located on carbon number 1. So when we bring everything together, we have the parent name, which is prop, the position of the triple bond 1, and then the suffix, which is yne, prop 1 yne. Some can also name it propyne. Whichever way you choose to name it is absolutely fine. And then the third step would be to indicate the position of the double bond, just as we did previously. So the number is always placed before the suffix. The number of the carbon atom that carries the triple bond is always placed before the suffix. So let's handle this example we're having on the screen. We have carbon number 1, 2, 3, and 4. The triple bond is located on carbon number 2 if we count from the left to the right. If we count from the right to the left, however, we're going to end up having 1, 2, 3, and 4. The triple bond will still be located on carbon number 2. So let's put our parameters in place. 4 carbon atoms gives us the parent name BUT, and then the triple bond is located on carbon number 2. When we bring everything together, we have the parent name, which is BOT, and then the position of the triple bond, which is carbon number 2, and then the suffix, which is "-ine", but2-ine, or buts. But2-ine is the name of the compound, as you can see. So proceeding further, we have a scenario where you have an alkyne that contains a branch. So somebody might be asking the question, how about if an alkyne has a branch? What do you do? Well, there are scenarios like that. When you have an alkyne that carries a branch, you give the triple bond priority. In other words, you number the parent chain in such a way that the triple bond has the lowest possible number. So what do we do in this case that we have an example to buttress what we're saying? We can number this compound now starting from the left. 1, 2, 3. We can decide to go down, which gives this one 4, or we can decide to continue going right, which gives this carbon atom number 4. Whichever way we choose is absolutely fine because we will not end up with a chain longer than 4 carbon atoms. 4 carbon atoms gives us the parent name BUT. Now, the next thing to do would be to determine our counting direction. Are we counting from the right to the left, or are we counting from the left to the right? If we count from the right to the left, we have carbon number 1, 2, 3, and 4. It means this triple bond will be resting on carbon number 3. If we count from the left to the right, we have 1, 2, 3, and 4. It means this triple bond will be resting on carbon number 1. So our counting will be from the left to the right because that is the counting pattern that gives the lowest number to the triple bond. So we have 4 carbon atoms, which gives us the parent name BUT, and then the triple bond is located on carbon number 1. And then finally, when we count 1, 2, 3, 4, we have a substituent or a branch over here, which is a methyl substituent, and it is located on carbon number 3. So how do we name this? We name this by starting with the substituent, and then we add the parent's name, and then we add the position of the triple bond, and then we add the suffix IYNE. So altogether, let's do that now. The substituent is methyl located on carbon number 3. So we have 3 methyl, and then the parent name, 4 carbon atoms, but, and then the position of the triple bond, which is on carbon number 1. So we have but, 1 ine, 3 methyl, but 1 ine would be the name of the compound, as you can see done over here. Now at this point, you might also be asking or thinking, what if there is a scenario where there is more than one triple bond present? If there are more than one triple bonds present, then you use this prefix di to identify 2 triple bonds and tri to identify the presence of 3 triple bonds. Now we have an example over here to buttress what we're talking about. Now, the first thing to do would be to number the parent chain that contains the carbon atoms. 1, 2, 3, 4. 4 carbon atoms gives us the parent name BUT. Now, what is the location of the triple bonds? The first triple bond is located on carbon number 1, and the second triple bond is located on carbon number 3. Now, if we decide to count from the right to the left, the triple bonds will also be located on carbon number 1 and carbon number 3. Let's check that out. 1, 2, 3, 4. You can see the first triple bond located on carbon number 1, the second one located on carbon number 3. So we have the parent name, which is 4 carbon atoms, that gives us BUT bonds. And then the triple bonds are located on carbon number 1 and 3. So when we bring everything together, we start with the parent name, which is but, and then we indicate the positions of the triple bond, which is 1, 3, and then we indicate the presence of two triple bonds using the prefix di, and then we add the suffix y, n, e. Let me rewrite that again. You can see it over here, but 1, 3 diyne, but 1, 3 diyne. So the rules are, you want to indicate the positions of the triple bonds and you want to separate numbers using a comma. I trust you're getting value for what's going on. Now, we're getting into a situation where we have not just a triple bond present, but we have a triple bond and a double bond present in one compound. When both a triple bond and a double bond are present, there is a particular way to carry it out. By the way, when a triple bond and a double bond are present in a compound, it is called an alkyne. Okay, that's the name for a compound that contains both a triple bond and a double bond. So there is a specific tie-breaking system we use to identify compounds that contain both a triple bond and a double bond. You can see what I just mentioned. It's called an alkyne or an enyne, whichever way you choose to identify them. So when this happens, the first thing you want to do is to choose the longest chain that contains both multiple bonds, that is both the double bond and the triple bond. So the parent chain must, number one, contain as many multiple bonds as possible. It must be the longest possible chain, including them. And then thirdly, if a longer chain leaves out one multiple bond, it cannot be chosen. Enough talk already. Let's see some examples right after we check out step number 2. Step number 2 would be to number the parent chain in such a way that we give the lowest possible sets of locants. Locants, we're simply talking about the position of the multiple bonds. So we number the chain such that the multiple bonds, that is the double bond and triple bonds, will get the lowest possible numbers, and then we compare the number sets. What exactly do we mean? Here is what we mean. A very good example is this. We have this compound on the screen. It contains both a double bond and a triple bond. So the first thing we want to do is to identify the parent chain. We have 1, 2, 3, 4, 5, 6. So to start with, we have 6 carbon atoms, which gives us the parent chain hex. Let's just keep this aside, okay? Now, the next thing to do would be to ask ourselves, what direction are we numbering from? We have both a double bond and a triple bond. Now, in this case, if we number from the right to the left, this is 1, 2, 3, 4, 5, 6. So numbering from the right, the double bond will be at carbon number 3. Let's indicate that. And the triple bond will be at carbon number 5. Let's also indicate that. 3 and 5. You can see the set 3, 5. But if we number from the left to the right now, we have 1, 2, 3, 4, 5, and 6. The triple bond will be located on carbon number 1, and the double bond will be located on carbon number 3, 1, 3. Now, my question to you is this. For right to left, we have 3, 5. And from left to right, we have 1, 3. Between 1, 3 and 3, 5, which of them is lower? Of course, 1, 3 is lower. So our counting direction goes from left to right in this case. Now, doing that, we have 6 carbon atoms, which gives us the parent name hex, right? Now, the position of the triple bond is located on carbon number 1, and the position of the double bond is located on carbon number 3. So let's bring everything together. We start with the parent name, which is hex. Now, we want to indicate the positions of the multiple bond. The multiple bond is we have a double bond, and to indicate the presence of a double bond, we use the suffix en, and then for a triple bond, we use the suffix yne. So let's indicate their positions. Now, which one do we start with? When we want to write the name of organic compounds and we're indicating the position of multiple bonds, we do so using the alphabetic order. Now, a double bond is indicated using ene and a triple bond is indicated using yne. Between the two of them, which one comes first in the alphabetical order? The double bond starts with letter E, triple bond starts with letter Y. So therefore, E will come first when we're writing the name. I'm sure you got that and you're not confused. So when we're indicating the position of the triple bond, that becomes 3 in, and then the position of the triple bond, which is 1 I. When you're indicating the position of a double bond, if it is not ending the name of the compound, you use en instead of ene. So altogether, the name of the compound becomes hex 3 in 1 I. That is how the compound is named. So now, step number 3 for naming compounds that contain both double and triple bonds is this. If there is a tie, that means if you number from left to right, and let's say you get the double bond to be on carbon number 1 and the triple bond to be on carbon number 3, that is, the set of numbers is 1, 3. And if you number from right to left, you still get the same thing. The triple bond will be on carbon number 1 and then the double bond is on carbon number 3, which is still 1, 3. Then the double bond takes priority. That is how it goes. Don't worry, we're going to do an example that shows exactly what it is I am talking about. So step number 4 is writing the name of compounds that contain both a double bond and a triple bond. So writing the name En, which is the double bond, is written before Yne. You saw that in the example we just treated. Alphabetical order determines the writing of the names, not the numbering priority. So this example we just dealt with now, the triple bond is at carbon number 1 and then the double bond is at carbon number 3. The parent chain contains 6 carbon atoms, which is hex, and you can see the name hex 3 in and then 1 I. So let's go ahead to check out some examples that we can handle using this concept. Right about now, we have an example on the screen that shows a tie situation. Now, what do we mean? We have this compound that shows us 4 carbon atoms present. 1, 2, 3, 4. We're numbering from the right to the left. If we number from the right to the left, the double bond is located on carbon number 1 and the triple bond is located on carbon number 3. That gives us a set of numbers 1, 3. If we number from the right to the left, we have 1, 2, 3, 4. The triple bond is located on carbon number 1 and the double bond is located on carbon number 3. Still the same 1, 3. So we have 1, 3 from left to right and 1, 3 from right to left. The question now becomes, which one do we pick? Now, since we have a tie, we'll give the priority to the double bond. Let me backtrack a bit and show you that rule. That rule says if there is a tie, you can see it over here. If there is a tie, the double bond gets priority. If both numbering directions give the same set of numbers, and we saw 1, 3 from left to right, 1, 3 from right to left, the double bond therefore will get the lower number. So it therefore means that for the example that we're checking out, counting from left to right gave us 1, 3. The double bond was located on carbon number 1. Counting from right to left also gave us 1, 3. the double bond was located or will be located on carbon number 3. So therefore we will go with left to right because we want to give the lowest number to the double bond that is present. This rule only applies if there is a tie, that is, the same set of numbers are given for both counting directions. So therefore, we're counting from the left to the right. The parent chain contains 4 carbon atoms, which is but, and then the positions of the multiple bonds. The double bond is located on carbon number 1, triple bond is located on carbon number 3. So bringing everything together, we have the parent name boots. And then the position of the double bond, which is carbon number 1, boots 1 in and then 3 I. This becomes the name of the compound. Boots 1 in 3 I. Boots 1 in 3 I. Now, somebody might be asking, okay, what if there are multiple bonds and then a substituent is also present? Okay, well, in that case, you want to give priority to the multiple bonds and then treat the substituent as the least prioritized. What do we mean? We have this structure over here that we want to name. So the first thing to do would be to obtain the parent chain. You can see this pattern just playing out with every video that we put out there. The parent chain is so important. 1, 2, 3, 4, 5. We can choose to go right again, 6, or we can choose to go up, which will still give us 6 carbon atoms. So whichever way we choose to do it, we have the parent chain to contain 6 carbon atoms, which gives us the name hex. Now the next thing to do would be to identify the position of the multiple bonds. If we count from left to right, 1, 2, 3, 4, 5, 6. This triple bond is located on carbon number 1 and the double bond is located on carbon number 3. That gives us a set of numbers 1, 3. But if we count from the right to the left, we have 1, 2, 3, 4, 5, and 6. The double bond is located on carbon number 3 and the triple bond is located on carbon number 5, 3, 5. For the first counting direction, we had 1, 3. For the second, we had 3, 5. So we're going with the first counting direction, which is from left to right. So doing that, we have 1, 2, 3, 4, 5, and 6. 6 carbon atoms. The parent name becomes hex. The next thing to do would be to identify the position of the multiple bonds. The double bond in this case is located on carbon number 4. You can see it. Oh, sorry, on carbon number 3, not carbon number 4. I beg your pardon, that was an error on my part. You can see it over here, carbon number 3. And the triple bond is located on carbon number 1. So we have 1, 3. The positions of the multiple bonds. Now the next thing to do would be to handle the branch, which is the substituent. The substituent is methyl CH3. Now CH3, which is the methyl substituent, is located on carbon number 5. So when we want to name this compound, we bring everything together. We start with the substituent and then we go on to add the parent's name and then we add the position of the multiple bonds and then we end with the suffix. So let's do it step by step. The substituent is methyl and it's located on carbon number 5. So we have 5 methyl. All right. The parent name is hex. Dealt with the substituent, we dealt with the parent name. Now the positions of the multiple bonds. We start by writing the double bond because it starts with the letter E, not the triple bond, we start with the letter Y. So the double bond is located on carbon number 3. So we have hex 3 in, and then the position of the triple bond, which is carbon number 1 I. 5 methyl, hex 3 in, 1 ion, dealt with the position and with the suffix as well. That's how the compound can be named. So now here is another example on the screen right now of a compound that we want to name. More and more examples flowing. So first things first, we have 4 carbon atoms. Okay, 1, 2, 3, 4. The parent chain contains 4 carbon atoms. That gives us the parent name BUT. The next thing we want to do is to identify the positions of the multiple bonds. If we count from the left to the right, 1, 2, 3, 4, this double bond is located on carbon number 1 and the triple bond on carbon number 3. That gives us a set of numbers 1, 3. So let's put that down. 1, 3. That's from left to right. If we count from the right to the left, however, 1, 2, 3, 4, we have the triple bond being on carbon number 1 and the double bond being on carbon number 3 as well. So we still have 1, 3 from right to left. So therefore, since we have the same set of numbers, the double bond will take priority in this case. So counting from the left to the right will be our counting direction. So counting from the left to the right, we have 1, 2, 3, 4. But is the parent name. The double bond is located on carbon number 1 and the triple bond on carbon number 3. So bringing everything together, we have boots. 1 in and then 3 I. That is the name of the compound, as you can see over here. Put 1 in and 3 I. So here are more and more worked examples. Let's go ahead and treat them individually. We have the first example over here, and let's go ahead and name it. So the first thing we want to do is identify the longest or the parent chain. So we have 4 carbon atoms, which gives us the parent name BUT. Now, are we counting from the right to the left or from the left to the right? Counting from the left to the right puts this triple bond on carbon number 1. If we count from the right to the left, we have 1, 2, 3, 4. This triple bond will be on carbon number 3. So our correct counting direction becomes from the left to the right. So that puts our triple bond at carbon number 1. And then the parent chain contains 5 carbon atoms, which gives us BUT but. So putting everything together, we have boots 1 I. That is the name of the compound. We have the second example. Have this compound on the screen right now. So we want to start off by counting the number of carbon atoms present in the parent chain. We have 1, 2, 3, 4, 5 carbon atoms. 5 carbon atoms gives us parent name pent. Now the question becomes, do we count from the right to the left or from left to the right? If we count from the left to the right, this becomes 1, 2, 3, 4, and 5. The triple bond is located on carbon number 2. If we count from the right to the left, this becomes 1, 2, 3, 4, and 5. Triple bond is located on carbon number 3. So the correct counting direction becomes from the left to the right to place this triple bond on carbon number 2. So therefore we have 1, 2, 3, 4, 5. The parent name becomes pent. And then the triple bond is located on carbon number 2, which gives us 2 yne. So putting everything together, we have pent 2 yne. That's the name of this compound. If you're getting massive value for this video, the least you can do is subscribe, like, and share to your friends who may be struggling with chemistry, particularly organic chemistry, because I'm going all out bringing videos that break down the concepts of chemistry every day, step by step. So we have this third example which contains a branch. Now remember, the triple bond or the multiple bond takes priority over the branch. So we want to first get the number of carbon atoms that are in the parent chain. So we can start from the left to the right. We have 1, 2, 3, 4, 5. or we can go from the left upwards. 1, 2, 3, 4. So we ended up with 4 carbon atoms left up. We ended up with 5 carbon atoms left to the right. So we're counting from the left to the right. Now, counting from the left to the right gives us this triple bond to be on carbon number 1. And we have 5 carbon atoms. That gives us the parent name pent. And then the triple bond is located on carbon number 1. So that gives us the name 1-ine. And then finally, we have the branch, which is this guy over here, methyl. Methyl is located on carbon number 3. So to identify the methyl, we use 3-methyl. So when we bring everything together, we start with the substituent plus the parent name plus the positions of the multiple bonds, and then plus the suffix. So let's begin with the substituent. The substituent is located on carbon number 3. We have 3-methyl plus the parent name. The parent name is pent plus the position of the multiple bond. The multiple bond is this triple bond located on carbon number 1. So we have pent 1-ine, 3-methyl pent 1-ine. That becomes the name of the compound. So here are some practice questions I'd like you to try out your hands on. It's been a long video with massive value already. So we have this basic section. Go all in and do them. Post the answers in the comment section and I'll be there waiting to receive them while I let you know if you're correct or you could use some corrections. So we have the intermediate section and we have the advanced section with loads of practice questions that you can try out your hands on. I'm looking forward to receiving your answers with more practice questions, more and more practice questions. So up next, we're going to be looking at functional groups. It's getting more interesting, by the way. My name is David, and all I do here is to help high school kids excel in chemistry. If this interests you, like this video, share, subscribe, and look out for more videos coming your way. With that being said,